People often ask why computer scientists need to study mathematics. While I can give lots of good academic reasons for this, the bottom line is that many interesting problems can be solved with relatively simple mathematics. In this podcast, we're going to talk about a mathematical technique called trilateration and ways computer scientists use it to build some well-known technology.
Trilateration is based on simple geometric ideas and is used to find the position of something. As an example, think about a point on a piece of paper. If you know that the point is 3 inches from the center of the paper, then you know that it lies somewhere on a circle that is centered on the page and has a radius of 3 inches. If you also know that the point you are locating is 6 inches from the top left corner of the paper, then you know that the point has to be one of the places where an arc 6 inches from the corner intersects the circle in the center. Now we know the point we are locating is one of 2 points. If we also know its distance from the upper left corner of the page, we will know its exact location. In general, when we are trilaterating the location of something, we know its distance from a number of known points. Each of those distances gives us a circle, or a sphere if we are working in 3 dimensions. The thing we are locating must be at a point where all of those circles or spheres intersect.
The Global Positioning System uses trilateration to determine your location in the world. It is based on about 30 satellites orbiting Earth. These satellites always know their position and transmit a signal every millisecond. This signal contains the position of the satellite and the exact time when the signal was sent. GPS receivers, like navigation systems in cars, receive those signals from as many satellites as they can see. Communication with a satellite requires a direct line of sight, so your navigation system won't be able to see all 30 satellites. Both the satellites and the receivers have very accurate clocks, and those clocks are used to calculate the distance from the satellite to the receiver. When the receiver receives a signal, it compares the timestamp in the signal with the current time. That difference tells us how long it took the signal to travel from the satellite to the receiver. These satellites travel at the speed of light, and physics tells us that the distance it traveled is the speed of light times the amount of time it was traveling. Therefore, the distance from the satellite to the receiver is the time the signal traveled times 3 times 10 to the 8th meters. Once it has a signal from a number of satellites, the signals it receives tell it the location and distance of the satellites. So the GPS receiver just has to perform trilateration to know where it is. The number of satellites required depends on the required accuracy and the intelligence of the system. When GPS systems are working in 3 dimensions, calculating latitude, longitude, and height above sea level, they theoretically require signals from at least 4 satellites. Some systems know the topography of the world and assume that the receiver is on the surface of the Earth, and therefore require 1 less satellite signal. Since there is some error in calculations, receiving signals from more satellites can improve the accuracy of the computed location.
In the cellular phone network, your calls are transmitted by radio signal between your phone and a cell tower in your area. At any point in time, your phone is receiving signals from multiple towers, and the signal from those towers degrade with distance. Therefore, your phone can use the strength of those signals to compute its distance from each tower. Knowing the locations of the towers, the phone can trilaterate its location. One of the challenges in the cell phone network comes from the fact that your phone may be moving while you're using it. As you ride in a car down the highway chatting with your friends, the cell network is watching your location. As you move away from one tower and towards another, it switches your call to be carried by that new tower. Under ideal circumstances, you get transferred from one tower to another as you talk, and you hear no more than a small pop sound during your call. However, when many people are in an area or the towers are far apart, this switch from one tower to the next may not be executed quickly enough, and your call can be dropped.
The U.S. government is building the Advanced National Seismic Systems to measure earthquakes in the U.S. This system will include over 7,000 seismic detectors on the ground and in buildings across the country. These detectors are sensitive to small shaking movements of the Earth's surface and can be used for, among other things, determining the exact location of an earthquake using trilateration. The challenge in locating the center of an earthquake is in computing the distance from the known locations. The detectors saw that movement to the unknown locations, the center of an earthquake. In all of our other examples, that distance was determined by the technology in the system, but that isn't true for earthquakes. We know that the strength of the movement caused by the earthquake lessens as the shock waves move away from the center, kind of like cell phone signal degrades with distance. However, we don't know the strength of that signal at its source, so we can't compute the distance directly. Instead, the system looks at the relative number of strengths of the signals at a large number of detectors and uses that information to calculate the center of the earthquake and its original strength. While the algorithm is slightly more complicated, it is still based on trilateration.
Trilateration can be used to find the locations of many things. All it requires is that you know the distance from a few known points and you can calculate your location. Trilateration is also a great example of the mathematics that computer scientists can leverage to solve interesting problems and to provide valuable technological services.